Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to practice writing the equilibrium constant. Let's jump in. Our equilibrium constant, KEQ, is written as products over reactants raised to their stoichiometric coefficients. Before we see an actual reaction, I do want to point out that our equilibrium constant is a capital K. Now, if you have already learned kinetics, you may already be familiar with a K, that is the rate constant, but I want you to notice that the K in kinetics is lowercase, it is a rate constant. The K in equilibrium is a capital K, and very often it is specified as a KEQ, or it will have some letters as a subscript after it. In chemistry, capitalization is actually quite important to identify what you are talking about. Now let's jump into a generic reaction. So we have a very generic reaction right here where our lowercase letters are our stoichiometric coefficients and our uppercase letters are whatever species we have in this reaction. It is in equilibrium. We have a forward rate and we have a reverse rate. We are going to write our equilibrium constant as products over reactants, and we're going to raise each one to their stoichiometric coefficients. So my KEQ looks like this. I have my concentration of my species C raised to its stoichiometric coefficient. Here is my species D. Here, again, it is raised to its stoichiometric coefficient. And the same is true with A and B. They are each raised to their stoichiometric coefficients. So when you are writing KEQs, or an equilibrium constant, first you must be very sure that you have a balanced chemical equation. It's a step that is very easy to overlook when you are given a chemical equation, but if you haven't balanced that chemical equation, you are not going to get the right coefficients. So there are two very common Ks that we use in equilibrium, Kc and Kp. Let me explain. Let's take our very generic reaction and we're going to put all of these species in aqueous solution. How do we write our K for this? Well, because these species are in aqueous solution, we are going to be monitoring their concentration. This is a Kc. C just simply for concentration. Concentration is also denoted by our brackets. And again, we are raising each of these to their stoichiometric coefficients right here. Now let me show you what a Kp is. Here is our same generic reaction, but notice these are all gases right here. We can measure gas concentration, that is absolutely a thing, but we can also measure gas pressure. This is a Kp. Makes sense, right? Kc for concentration, Kp for pressure. In this case, I don't use brackets, I use parentheses. Brackets generally are reserved for concentration, and I'm measuring pressure here, but everything is still to their stoichiometric coefficient here. So having a balanced chemical equation, as usual, is very important. Okay, enough with the generic equations. Let's do some real equations. We need to write the equilibrium constant for this reaction right here. The first thing I want to do is I want to check and make sure that it is balanced properly. So I have 2 nitrogens and 2 nitrogens. I have 6 hydrogens and yes, 6 hydrogens. These are all gases, so I'm going to write a Kp for pressure. Here is my Kp. I have the pressure of my products, my ammonia, my NH3. Of course, that is squared because I have a 2 in front of it. That is going to be over my reactants, which are hydrogen gas, which is going to be cubed because I have a 3 here, and nitrogen gas, which we don't write it in, but is raised to the first power because, of course, as we did not write in here, there is a 1 right here. Initially, you might find it helpful to write that 1 in just so that you know that everything is raised to its proper power, but generally we don't put the 1s in. Let's do another one. We need to write the equilibrium constant for this reaction right here. You'll notice these are all aqueous, so these are all in solution. I am going to write a Kc for concentration. But before I write my Kc, let's check and make sure that this is a balanced chemical equation. I have 1 sodium and 1 sodium, same with aluminum, 1 and 1. And chlorines, I have 3 plus 1, which is 4, and yes, I have 4 right here. So yes, balanced chemical equation. Now I'm going to write my Kc. Here it is right here. Again, I'm using brackets because these are concentrations. And you might say, where are all your powers? Well, this equation is 1 to 1 to 1, which means all of my exponents here are 1, which again, you don't have to write in. Let's do some more examples, and I want to show you a couple of things that K can do. Okay, starting with our reaction right here, we want to get a Kc for this. Now I did specify a Kc even though we have gases. Again, that's perfectly fine. You can measure gas pressure or you can measure gas concentration. And in this case, it's specified concentration. Making sure I have a balanced chemical equation. I'm seeing 2 sulfurs, 6 oxygens, and 4 oxygens plus 2 oxygens is 6. Okay, so yes, our equation is balanced correctly. Here is our Kc. We have our products over reactants. Our SO2 is squared, our oxygen is to the first, and our SO3 is also squared. But what would happen if I took this reaction and instead of writing it as SO3 going to SO2 and O2, I wrote it reverse? Okay, so here's the same question, but you can see my reaction has been reversed. My products are now my reactants, and my reactants are now my products, which is totally valid. Remember, this equation is in equilibrium. We have a forward and a reverse reaction happening. How would I write the Kc for this? It would look like this right here. I'm going to call this Kc1 just to differentiate it from Kc up here. This time my product is SO3 and my reactants are SO2 and O2. Of course, my powers here do not change because my balanced chemical equation is still balanced the same way. But obviously there's a relationship between this Kc1 and this Kc. They are reciprocals. So Kc1 is just equal to 1 over Kc. So your forward and reverse reactions, the K's are reciprocals of each other. Let's do something else with this equation. All right, here is the Kc for this equation right here. Let's compare it to our original equation. We still have products and reactants the same, but what have I done with this modification? I've multiplied everything through by 2. I'm going to call this Kc2, again, just to differentiate it from Kc and Kc1. But this time my SO2 is raised to the 4th. Again, I'm just following my stoichiometric coefficients here in my balanced chemical equation. But there's definitely a relationship between Kc2 and Kc, and it's not multiplied by 2, it's actually squared. So remember, your coefficients in your balanced chemical equation go to exponents here. Just to summarize these two rules, the equilibrium constant for a reverse reaction is the reciprocal of the original equilibrium constant. This is what we saw right here. So K reverse is equal to 1 over K forward. This is really handy when you need to flip an equation. Our second rule is when an equilibrium reaction is multiplied by a factor n, the original equilibrium constant is raised to the nth power. So again, up here we took our original equation and we multiplied through by 2, so we raised the Kc to the second power. Generically, this is going to be KEQ for our new reaction is going to be our original KEQ raised to whatever n is. Okay, still going on with more things that K can do. We've talked about Kc and Kp. Is there a relationship between those two? Yes, there is, and we can convert between Kp and Kc. The equation for this is given right here. Kp equals Kc times RT to the delta N. Okay, so let's define what all these terms are. R, you may recognize from your gas laws, that is the universal gas constant. We most commonly use this 0.08206 liters atmospheres per mole K. Our T here is temperature. Temperature must be measured in Kelvin. This is because our R measures temperature in Kelvin. Again, units must match. Our delta N is our change in moles. Now this is different for every reaction. What you're going to do is you're going to sum the coefficients of the products and you're going to subtract it from the sum of the coefficients of the reactants. Again, critical that you have a balanced chemical equation. Let's actually work a problem for a specific equation. All right, Kp for the following reaction is given as this number right here, 2.9 times 10 to the negative third. This is 1 over atmospheres, and it's at 25 degrees Celsius. Okay, and we're given our chemical equation right here, and we just want to calculate the Kc. First, is my equation balanced? So carbons are balanced, oxygens are balanced, and chlorines. Okay, so this equation is balanced. It's a 1 to 1 to 1. Let's use our formula here, and let's calculate Kc. Just rewriting my formula right here. I am first going to calculate my delta N. I call these side calculations. So remember, your change in moles is the sum of the coefficients of the products minus the sum of the coefficients of the reactants. Well, what are my coefficients for my products and my reactants so I know what to subtract? Remember, I have ones in front of all of my species here. This is a 1 to 1 to 1 ratio. And I just need to sum these coefficients. So on my product side, that's easy because I only have one species. The sum of the moles of the products is 1. So I'm going to have 1 for my sum of the products. For my reactants, I do have 2 species, so I'm actually going to do a little bit of adding, but they're each 1. So that is simply 1 plus 1. So my change in moles is -1. And yes, that is totally fine. Sometimes you will end up with a positive delta N, and sometimes you will end up with a negative delta N. It just depends on the balanced chemical equation. Now let's plug in my numbers for my equation right here. I was given the Kp, so I'm just going to straight up put that in here. I'm solving for Kc. Again, my R is my 0.08206. This is liter atmosphere over mole K. My temperature is 25 degrees C, but that is in Celsius. We need it in Kelvin. Thankfully, that's an easy conversion. That is 298 Kelvin. Again, it's important that your units cancel here, which is why we cannot be in Celsius. And finally, I'm going to raise this quantity to the delta N, or the -1 in my case. It is important that you put your parentheses in the right place, so do not include this Kc in your parentheses. That is raised to your delta N. So now I'm going to simplify. I'm going to simplify this term right here, and I get 0.04089. Again, you can see my units have changed right here because my Kelvin has canceled out. Now just to solve for Kc, I get Kc is equal to 0.071 liters per mole. And yes, that means my atmospheres did cancel out. A common place to get tripped up when you're doing this conversion is first not starting with the balanced chemical equation. That is going to give you the wrong value for your delta N. And the other place students get tripped up is units, either not converting Celsius to Kelvin. One more thing I want to show you about K, and this is what the value of K can tell you about the reaction. Okay, so I'm going back to what's now our favorite reaction right here. Here is our Kc, like we've done several times over. So what will be true about K if the products of this reaction are favored? So if your amounts of products are always going to be higher than your amounts of reactants. Remember, your amounts do not need to be the same, they just need to be constant at equilibrium. Well, if my numerator is going to always be larger than my denominator, it means that KEQ is going to be greater than 1. So when the products of a reaction are favored, the numerator dominates the expression for KEQ, and KEQ is greater than 1. So you can tell just by given a K whether your products or your reactants are favored. If K is greater than 1, your products are going to be favored. Okay, so what happens when the opposite is true? So when the reactants of the reaction are favored, the denominator is going to dominate your KEQ. This is going to give you a KEQ of less than 1. Again, if your denominator is really big, then your KEQ is going to be quite small. So before you even start any calculations with KEQ, it is helpful to know, hey, are my products or my reactants favored in this reaction? And here is a table to help you summarize what is going on with KEQ. There is one other thing that I want to mention. KEQ is never going to equal 0. A KEQ of 0 means you have no products, which means you have no reaction. So you cannot establish equilibrium if you have no reaction. And that is all the really cool things that you can do with K, that you can figure out with K, even before you're doing any major calculations. I hope you found this video helpful, and thanks so much for watching.